Welcome. This is a sphygmometer. It's an analog device used to measure blood pressure. You may recognize it. In a sphygmomanometer, the pressure is exerted by a small hand pump, which transfers into the cuff, which is wrapped around a person's arm. The pressure exerted by the person's bloodstream pushes against the tubing connected to the sphygmomanometer, putting pressure on it. The pressurized air enters the corrugated diaphragms, and they deflect with the pressure. The deflection moves the piston, thus turning the gear system, moving the needle. There are two types of diaphragm capsules, conventional and nested. The diaphragm capsules in the sphygmomanometer are conventional, which means that their corrugations are mirrored instead of overlapping. The corrugation has two purposes, the first of which is increased surface area, which increases sensitivity, and the second is that the corrugation increases the linear region of deflection against pressure.
So the air inside the sphygmomanometer is a quiescent fluid, which means there is no flow. A lot of non-dimensional parameters become unimportant. We don't care about the Reynolds number. We don't care about things like viscous losses. We don't care about flow models. It doesn't matter whether the flow entering is turbulent or laminar because it doesn't affect the pressure. We do know the air is compressed. We also know it is an ideal gas or can be modeled as. In terms of the force that deflects the diaphragms, you can use this integral equation here. But for diaphragm, that simplifies down to the force is equal to the effective area times the pressure, or the effective area, the circular area times the ratio of these two constants. As you can see, there's the small deflection constant and the flexural force constant, quadratic relationship with Q, which is a ratio of height of the corrugation to the thickness of the diaphragm.
Deflection of the diaphragm caused by the force, as described the integral of P dotted with the unit normal integrated over the effective area of the diaphragm, is a main feature of this device. To begin discussing the deflection, we will start with the simple case of flat diaphragm. For flat diaphragms, the deflection is governed by the equation on the left, where A is the radius of the diaphragm, C is a constant based on the boundary conditions, delta P is the pressure difference, T the thickness, and E the Young's modulus. Deflection of a corrugated diaphragm is governed by the equation on the right, where A is the radius of the diaphragm, delta P the pressure difference, T the thickness, and E the Young's modulus. AP, BP, KP, and LP are numeric constants that depend on the geometry of the diaphragm. AP is a dimensionless stiffness constant for small deflections, BP is a dimensionless stiffness constant for large deflections, KP is the bending stiffness constant, and LP is the tension stiffness constant. This equation is nonlinear in delta because as you deflect the diaphragm, tensile stress in the plane of the diaphragm will build up. A diaphragm under tension will be stiffer than without, thus leading to a nonlinear relationship between the pressure applied to the diaphragm and its deflection. Both of these equations assume that the boundary conditions for the plate are fixed, which is true for our device because the two diaphragm plates are welded together. Now, to further discuss the variety of constants used in the corrugated deflection equation, the shape factor, Q, is a dimensionless parameter defined by the relationship between the thickness of the diaphragm wall, T, and the height of the corrugation, H. AP, the stiffness constant for small deflections, is defined as shown using Q, the shape factor, and mu, Poisson's ratio. BP, the stiffness constant for large deflections, is defined in terms of AP and Q on the slide for the sake of neatness. We need to use both AP and BP because the deflection of the diaphragm in our device is large compared to the radius of the diaphragm. All of the sources we have found have stated that the additional two constants, LP and KP, used to derive the deflection of the diaphragm are taken from graphs or tabulated data. These graphs show that as the ratio between A and B increase, both LP and KP increase for a section of shape factors, shown as families of curves on each of these graphs.
So how we go from deflection of the diaphragms to a pressure reading that we can read and use. The deflection produces a linear motion here at this lever arm that rotates these two gears. Here's the lever arm. You can see a deflection X. You can use trigonometry to solve that to find theta A, the rotation of the first gear. That'll turn this gear here. As you can see at this gear interface, there is a spring right above it that does resist rotation of the dial, but it has a really low spring constant, and its purpose is really just to make sure that these two aren't like wobbling around as they turn. So we can ignore it, and we can also ignore friction. This just becomes a gear ratio problem. The gear ratio of these gears is about 7.65. The needle turns back theta B. Each degree it turns corresponds to about 0.9 millimeters of mercury.
So why this size? Looking at the deflection equation, we can see that increases in the material thickness T cause decreases in sensitivity. Similarly, increases in the corrugation height H cause decreases in sensitivity, though the corrugation increases the linearity of the response. We can then look at the outer and inner radii of the corrugated section of the diaphragm, A and B. Increasing A increases the deflection about the fifth power, given that B over A factors into KP and LP. Increased B decreases the deflection at about the first power because B appears only in KP and LP. Stacking more capsules saves space because A can be smaller. A can only be so small because B has to be big enough to let air through membranes, and B over A needs to be small. It's easier to have two capsules. The number of corrugations changes the properties subtly, but those effects are minimal.
Hi, Professor Kirby.
Sphygmomanometer.
Is a sphygmomanometer. Next to the sphygmomanometer, putting the sphygmomanometer is a sphygmometer. And a sphygmometer, sphygmometer. Yeah. Is a sphygmomanometer.
Shown here. Because increases in the plane, the tensile stress means that it relates determined from graphs.
The diaphragm turns the dial. The device is an example of quiescent fluid, which is that the fluid is not moving at the time we analyze it. You can use the ideal gas law to find changes in temperature here, but if taking your blood pressure results in large changes in temperature, low blood pressure is the least of your problems.
In the I feel like that was better in terms of bloopers too.
Sphygmomanometer.